This is the brief on the physics of supercooling. You know that strange state where liquid water gets colder than its freezing point, but it doesn't actually turn into ice? Well, that's supercooling. And it isn't just a cool party trick. Understanding how to stop ice crystals from forming is absolutely crucial for things like cryogenics, to keep cell walls from getting shredded when we try to freeze and revive living tissue. Okay, so first, you've got to understand that ice crystal formation is basically a battle between the inside of the crystal and its skin. The interior really wants to lock into place and freeze. But the surface, that boundary with the liquid water, it pushes back. It just takes too much energy to form. Second, for freezing to actually happen, a crystal has to hit a critical tipping point size. See, if it's too small, its surface is proportionally huge, and that resistance I mentioned just wins out. So the crystal melts right back down. That's why a sudden jolt or even a speck of dust can be enough to kickstart the whole process. And finally, it turns out you can stop freezing altogether with pressure, but only in really tiny, rigid containers. Since water expands when it freezes, squeezing it into a microscopic container that won't budge creates immense pressure. This pressure becomes this powerful third player that just overwhelms the ice's desire to form. It stops it cold, no matter what size it is, even if you smack it. So supercooling is all about managing these competing forces. But it seems that extreme pressure in tiny, rigid spaces can create a guaranteed barrier against ice ever growing at all.